at the University of Vienna in the Department of Environmental Geosciences, or EDGE. There's a web page on the top of the slide. This somewhat bulky, long title was my attempt to find an umbrella for what I would like to talk about today. I will try to, at the beginning, introduce you to some stuff that many listeners in the audience probably are familiar with, but just in case some are not, I would like to first start with some basics, and then I will mainly focus on this group of so-called emerging contaminants that are often ionic or ionizable, which means they can have a charge, and we'll talk about that a little later. Yeah, so what probably 95% of you know is what biochar is. I would like to specify it slightly for this talk. So when I talk about biochar here, I exclusively refer to plant biomass-based biochar, so the product of pyrolysis of plant residues, so stuff like wood or grasses or something along those lines. So I'm not talking about manure or sewage sludge or other stuff that could also be pyrolyzed, and some would also call biochar perhaps. So as most of you know, if we pyrolyze biomass, we have this carbonization process, and what we get is a highly carbonized material depending on how high the temperature is. And this highly carbonized material has a relatively strong sorption potential for organic pollutants, which is the key topic that I'll be talking about today. So just to contrast this a little bit with what is commonly understood for activated carbon. So if we look at commercial activated carbons, the overwhelming majority, so something in the range of 95% or higher of activated carbons that you can buy are actually based on either fossil coal or charred coconut shells. And those materials are then activated, so they are heated up usually, and then if they are physically, quote unquote, activated, we use some water steam to increase their porosity and some surface functionalities, or we can use chemicals such as the acids and the zinc chloride here. I will later shortly mention some alternatives, because both of those feedstocks are not necessarily very sustainable if we are talking about green carbon, and if we are talking about the sustainability aspect of remediations and of pollution control. And then obviously fossil coal, I don't need to explain why that is not particularly sustainable, but also the charred coconut shells are somewhat of an issue because they almost exclusively are almost exclusively grown and collected in Southeast Asia, and very often they are bought pre-charred by farmers, which is not always done in the most healthy and secure environment, and they are a limited resource as well. And actually, I talked to some activated carbon producers last year who said that actually the coconut shell market is already getting stressed to a degree. So both of those are probably not the most sustainable materials we could think of. What makes activated carbons and biochars to some degree similar is their underlying chemical structure. So all of them have highly condensed aromatic sheets as a ground structure. And as you can see here, this was a paper where they actually observed the aromatic clusters in biochar at the nanoscale. And as you can see here, there are those aromatic clusters in there. Depending on what feedstock we use and what production conditions there are, obviously those aromatic clusters might be more predominant or less predominant. But this chemical structure of having very large aromatic sheets is something that unites all of those materials. And what makes them decent or good sorbents for organic contaminants is, on the one hand, that because of those structures, they can have a lot of micro and mesopores. So those are pores in the lower micro and upper nanometer range. And in addition to that, their high aromaticity, which enables them to undergo specific interactions particularly well with aromatic compounds such as PAHs. So PAHs are of course also a group of compounds that most of you know. So here in the image you can see pyrene. This is just a study we did a couple of years ago where we actually mixed some compost and some biochars into soils with different pyrene concentrations, and we did some ecotoxicology tests to show that when the pHs are bound to the biochar, they are actually not really bioavailable anymore, whereas if they are bound to the compost, they can still be uptaken. So if you look here, the C is the compost, the B is the biochar, and the B plus C is the biochar and the compost. You can actually see that if we look at the toxicology here, there is not a very largely observable trend here, but we do see that those two are slightly lower than the ones where biochar is present. But at the higher concentrations, we see a very clear difference that the compost did not really make a difference at all, even though sorption increased, whereas the biochar clearly reduced the exposure to this contaminant. That is because the pHs are bound more strongly to the biochar compared to the compost. Now, if we take it slightly a step wider, a step more towards the polarity that I want to talk about later, in this other study we also published a couple of years ago, we looked at a range of pHs as well as nitrogen, sulfur, and oxygen substituted pHs. And you can actually see here, this is the fluorine, and then this is the carboxyl with the nitrogen atom here, and we have the dibenzothiophene with the sulfur here, and then dibenzofuran with the oxygen here. And we can actually see that the nitrogen substituted molecule, which is the green one here, sorbs really strong compared to those other structures that look all very similar. And this is because on most biochars and activated carbons, we have mainly a negative surface charge. We have lots of oxygen containing functional groups. And this nitrogen is a partial positive charged molecule, this nitrogen substituted carbazole, which can undergo, among other things, good strong hydrogen bonds with those oxygen surface functional groups. Okay, so this is stuff that I assume most of you to some degree are familiar with and know. We all know that biochars sorb pH as well and so on. And we know about actual field applications in this direction already. So what I would like to talk mainly about today are the others. So all of the compounds that are not so-called legacy contaminants, so-called hydrophobic neutral organic contaminants. And some call those emerging contaminants, even though we have been working on them for about 20 years now. So let's just call them the others. So if we talk about pharmaceuticals or plant protection agents or industrial chemicals, very often those molecules are not neutral and hydrophobic, or not exclusively neutral and hydrophobic. And actually very often those molecules contain acidic or basic functional groups. And what makes acidic and basic functional groups somewhat exciting is that depending on the pH, they change their species. So for acids at very low pH, we have a neutral compound that would behave like any other neutral compound. And if we increase the pH above the pKa, which would be about here, we get a negatively charged compound. And in contrast, with bases at very low pH, we would have a positively charged compound, and above the dissociation constant, we would get a neutral compound. So depending on pH, the behavior of those compounds will change, and their potential to interact with our biochar activated carbon, of course, would also change. To make this slightly more concrete, to put some numbers on this, if we look at this new proposed contaminant class, the persistent, mobile, and toxic, and very persistent and very mobile contaminant class, which is kind of a new umbrella term for all of those compounds that are highly mobile in the environment and are of quite some concern, especially for water providers. If we look at those compounds, there is a SIN list at the bottom of the slide here, which are kind of high priority PMT substances. And out of the entries in the SIN list, 27 of 34 are ionizable or ionic. And if we zoom out a little bit and look at all the compounds that are registered under the European chemicals regulatory framework REACH, almost half of all substances registered there are ionizable or ionic. And most of those ionizable or ionic compounds are negatively charged, so 27%. And here, just as an example, we have the melamine, which could have a positive charge on this nitrogen here, and we have the PFAS here with a potentially negative charge here. So let's scale down and look into what happens at the surface of our carbonaceous materials. So a couple of years ago, we published this review where we tried to pin down all the potential interactions that can occur. So as you can see, it depends not only on the speciation of our molecule, of our compound, but also on the speciation of our sorbent, of our biochar or activated carbon. And the kind of a similar parameter to the dissociation constant of the sorbate is the point of zero charge of our material, of our sorbent. So above the point of zero charge, our sorbent will be mainly negatively charged, and below it will be mainly positively charged. And accordingly, the different combinations will yield different potential interactions. So we have those pi-pi electron donor acceptor interactions, of course, that we know from neutral compounds anyway. But if we go to the charged species, we can have different types of interactions. We can have the charge-resisted H bond. We can have cation bridging with divalent inorganic cations such as calcium. And similarly for positively charged compounds, so for bases, actually we get electrostatic attraction if the material is negatively charged and our compound is positively charged. So we can have a variety of additional interactions with those surfaces. And to make it even a little bit more complicated, if we have Zwitter ionic compounds, all of the stuff can basically happen at the same time. Now, what does this mean on a practical level? Well, in a project together with the Ithaca Institute, EAWAG, and Agroscope in Switzerland, we looked at using wood-based activated carbons and biochars as a fourth purification stage. So as some of you might know, there is a new regulation in Switzerland that actually demands an additional purification stage for the effluent from wastewater treatment plants. And one of those possible purification stages is, of course, the use of activated carbon. So in this project, we looked at a relatively long list of 15 compounds that have been selected by the Swiss regulatory agencies to be of concern in this context, and to look at the removal of all of those compounds using different materials. And we actually compared those to two commercial activated carbons. So the carbopal is a coconut shell-based activated carbon, and the norit is a fossil coal-based activated carbon, as far as I recall. And you can see here to the right of those two kind of commercial state-of-the-art activated carbons, we can see a beech biochar, which is clearly outperformed by those activated carbons. But if we actually pyrolyze our beech with different amounts of oxidants, such as water, so steam, we actually can get a similar performance to the commercial activated carbons with a wood-based, more or less sustainable activated biochar, which is a good thing to know. Now, if we slightly zoom in, so here we have those different types of indices that we used. So we had a reduction in UV absorbance, a reduction in DOC, and a reduction in organic micropollutants. So if we want to focus a little bit more on those micropollutants, if we zoom in, we can actually see that the negatively charged, so the minuses here, they tend to sorb slightly less than the neutral ones, are the circles, and the positively charged ones tend to sorb the best. And this again is partly simply because of electrostatics, because as our activated carbon or our biochar is somewhat negatively charged on the surface, obviously negatively charged compounds will have a harder time reaching a sorption site compared to neutral or positively charged compounds. Now, all of this is nice and good, but obviously it would be great if we would have tools to actually predict what compound sorbs how well to our carbonaceous material. So how can we predict ionizable organics sorption to those materials? And this is actually a quite challenging question, because all of those additional interactions make it somewhat complicated to find good and solid prediction tools, because those interactions depend on so many additional factors: ionic strength, pH, and of course also organic carbon content in the solution. So what we did is we collected lots of literature data. We collected hundreds of papers and extracted the data from those papers. And then we parameterized a neural network approach to basically let the machine learn how to predict those sorptive interactions. And what we found is that in order for us to get good predictions, as you can see here, we had to divide our compounds into two groups. So our neutral, polar, as well as negatively charged compounds were in one group. And as soon as we have a positive charge in our compound, we had to make another group for those compounds. And the reason for this is quite simple. Basically, as soon as we have a positive charge in our compound, in our molecule, that positive charge will kind of outperform all the other factors in importance, because it will be electrostatically attracted to our surface, whereas the other factors are less, pulling less, so to say. So to make those black boxes a little less intransparent, what we did is we basically used those predictive models, and we generated a very, very large amount of theoretical scenarios where we predicted sorption. And this very large amount of theoretical data we then used to run a so-called global sensitivity analysis. And this global sensitivity analysis can basically be used to determine which are the most important factors for sorption. And as you can see here, all the blue factors are kind of solution or biochar parameters, and the other colors are compound parameters. And as you can see, for the anion and polar group, the polarizability, so the capacity to undergo pi-pi electron donor acceptor interaction, was quite important. So that would be the green one here. In contrast, for the cations and zwitterions, all of the material parameters appear to be much more important than the compound parameters. However, there might be some bias here, because first of all, there are way less data available for those kinds of compounds. And second of all, most studies don't report some key parameters. For instance, the cation exchange capacity, which would be key for this electrostatic interaction, is very rarely reported. So we could not really use that in our literature-based predictive model. So that's something that one would want to change in the future. So to kind of try to wrap this up, because I see the time is running, biochar and activated carbon do have a role to play to sorb, to immobilize, to get in control of those persistent mobile and toxic substances. However, many carbonaceous materials do struggle with many of those compounds, especially if they are not aromatic. I showed you for the negatively charged compounds now that those pi-pi electron donor acceptor interactions are really important. And several of the priority PMT substances, such as the PFAS, the trifluoroacetic acid, as well as the 1,4-dioxane, those are all non-aromatic, and all of those are basically hardly removed or sorbed by carbonaceous materials. So we should keep in mind that biochars and activated carbons are great sorbents for many compounds, but not for all. And with that, I look forward to getting some questions from you guys. And I will stop the screen sharing so I can see someone, I guess.
Thank you very much, Gabriel. That's a really nice and interesting topic, and kind of impressive work you've already done. So for anyone who has a question, please, you can either unmute yourself or write it in the chat function, which you should see at the bottom of your screen. And for me, I have one question that came up in my mind. So would you say that biochar composites might present an advantage as a sorbent, so to have positively and negatively charged surfaces in one material?
It depends, of course, on what your aim is, right? So if you want to immobilize anions, let's say arsenic, so to go in the inorganic sphere, but also for organic anions, it can be of some use. But honestly, you could go, like if I were just a remediation practitioner, you could go for anion exchange resins, for example. So for organic anions, basically, as soon as you don't have some kind of an aromatic structure where our biochars and our activated carbons have this advantage of undergoing those pi-pi electron donor acceptor interactions, as soon as you kind of cut those out, there is not a very large advantage of using a carbonaceous material to other methods that might be more efficient.
Okay, thank you. So Shemislav is asking, can you provide any insights regarding production parameters and the sorption ability of the biochars you used? So I guess the activated biochars you produced.
Yeah, the paper is published, so I'm happy to send it around to anyone who doesn't have access to it. That study was led by Nicolas Hagemann from Ithaca, and generally speaking, the activation happened at 900 degrees. So the pyrolysis unit was used at 900 degrees, and then those activation agents were kind of sprayed in. So, for example, some water steam was sprayed into the chamber. So the residence time, I would have to check. I don't know it by heart.
Okay, so I can check the paper and send it in the chat afterwards. Another question from Mitchell was, does porosity and nanosize of surface openings impact the adsorption capacity? I guess we saw that the surface area itself has an impact, but yeah.
It most definitely does. So if, for instance, in one of the studies that I showed at the beginning, where we looked at those different types of PAHs, there we actually saw that the degradability of our compounds kind of inversed. So if we did not have biochar in our system, it was what you would expect, that the larger kind of chubby molecules were degraded more slowly than the small ones. But when we had biochar in the systems, what we actually observed is that the smaller molecules were comparatively hard. It was comparatively harder for the microbes to degrade the smaller molecules, because there is some kind of steric hindrance to the large molecules to reach some of the sorption sites. So yes, the pore geometry definitely plays a role. Yeah, I hope that answers the question.
If not, please
please reach out to me or write me an email. Yeah.
So the next question comes from Paula. How important do you think is to know the charge details for gas-solid reactions rather than liquid-solid reactions? Do you think, for example, aromatics in gas phase could be easily adsorbed by biochar?
I have to say that I myself have rarely worked with gas adsorption, but generally, yes, aromatics in the gas phase should be removed relatively easily. The charge, the importance of the charge will not change. So if I have a negatively charged compound in the gas phase, it will still be electrostatically less favorable for it to go to the biochar compared to a positively charged molecule. So that would be my guess, but I'm not a gas expert.
And two more questions from Tom. Do you have useful data for biochar, not necessarily activated carbon? Okay.
How do you define useful?
I'm not sure how you should answer that.
Maybe Tom, you have to write me an email and explain what useful is.
And the second one, what is the effect of cation exchange capacity of the substrate on its ability to strongly adsorb certain ions or molecules?
Well, this is something that I also know of some unpublished data, and there are some unpublished data also in our group. It is very clear that if we talk about ionic molecules, the ion exchange capacity is a key parameter, and this is very rarely reported, unfortunately, in many sorption studies, even if they use ionized molecules in their study. And what comes, what on top of that, as soon as we have those ionized species, the competition with inorganic ions, salts, calcium, magnesium, all of those ions, the competition with those ions can also become important, which is something that is also rarely discussed. But if we talk about ionized molecules, the ionic strength and ionic composition in our pore water also becomes quite important. So higher cation exchange capacity basically means that more cations will be immobilized. That's what you can kind of assume with a relatively high confidence.
And I see that John raised his hand. Please. Yeah.
Hi, good afternoon, everybody.
Hi, John.
Gabriel, when you did the comparison of activated biochar compared to the commercial activated carbons, did you look at the other characteristics just in terms of particle integrity, hardness, regeneration capability, and the tendency to go to powder and block the sieves?
Yeah, so the tendency to become a powder was not an issue here because we actually use it in a powdered form. So that's the process. Actually, this was done with real wastewater treatment water. And right now there is a follow-up project going on where we have like a kind of medium scale wastewater treatment plant where actually the powdered activated biochar is used. So the becoming a powder in this case was not a concern. Regarding the physical stability, more generally, that was not like a key criteria for us, again, because of the powder stuff. And regeneration is looked at right now to some degree, but I don't have the data to show right now.
Okay, if John is happy, then I think we are perfectly on time. Thank you very much for that, Gabriel. Great presentation. And I think if there are any questions coming up, please, Gabriel, if you can answer in the chat, that would be great. And otherwise, thank you again.